Greetings of the day. Welcome back to the series on control systems engineering. Today we are here with the third lecture on this module of control systems engineering. Now, this lecture consists of some mathematical preliminaries, some basic ideas which we must consider before proceeding forward and trying to understand the logics of control system. Now, the overview. We'll see what an ordinary differential equation is, or rather say we will um, present a set of revision on that. We'll see a review on Laplace transforms, which you might have already seen in basic mathematical or mathematics courses. We'll see something about singularity functions and their significance in control systems engineering. We'll show some examples of Laplace transforms of certain signals. We'll see the properties of Laplace transform, varying all the way from linearity, time scaling, time shifting, frequency shifting, time differentiation, and convolution. So let's begin. Now, an ordinary differential equation. So the system that we would tend to observe in this domain of control system engineering is supposedly a linear, time invariant, causal dynamic system. So from the first lecture, you would have a basic idea of these natures of systems. And when I say a linear, time invariant, a causal, and a dynamic system, these are basically the same system I'm talking about. Now, these sort of systems are generally identified by ordinary differential equations. Now, when we would say if the system is linear and it is represented in form of ODE, it will be done in form of a linear ODE with constant coefficient. Now, if I mean a linear ordinary differential equation, I would say the system is linear, and I'm saying that the coefficient would be constant or a non-variant coefficient, then I mean the system is time invariant as well. So as a whole, the system of our choice, that is a linear, time invariant, causal dynamic system, it would be given as a linear ordinary differential equation which has constant coefficients. Now let's have a look onto this. So I assume you are well aware of an homogeneous ordinary differential equation. So any homogeneous ordinary differential equation of the form as shown here, dy over dt plus ay of t equals 0. Now this can be solved in form of exponential function. This is well known by the basic preliminary mathematical courses that you have been through during the first year of engineering, and for some branches in the second year of engineering as well. However, we would know that for a homogeneous ordinary differential equation, exponential function, it's the only solution wherein the coefficients are constant. Say, observe here, for this particular expression, for this particular equation here, a is the coefficient which is constant here, and we have 1 here, which is another constant. So we would say this kind of ordinary differential equation is sufficient enough to represent the system of our choice while dealing with this particular subject. Now let's assume an inhomogeneous ordinary differential equation. In the previous case, you would have noticed one side of the equation, it equated to 0, wherein now in terms of control engineering, we would understand, assume there is a system which is static, as in which is stable, and there is no perturbation given to it. That is, there is no change given to it. Those type of systems would be represented as homogeneous ODE. Whereas if you are expecting to observe the response of a system by defining, say, certain sort of perturbation, maybe you'd say so certain change, maybe in the input that you would have chosen. If you apply certain change to the system, you would be representing this particular dynamic of the system in terms of an inhomogeneous ODE, ordinary differential equation. And the basic form is given over here, wherein this left hand side is similar to what we saw in the earlier case, the homogeneous ODE. But in the right hand side, you observe this particular B u of t. Now, for this particular moment, keep this in your mind. And later in this series, I'll be explaining you what exactly is the need of this particular signal over here and how exactly that affects the dynamics of the system. Right. For an equation, an inhomogeneous ODE, the solution will look something of this sort, wherein this particular segment over here, you would notice this is similar to what we observed in the previous case of homogeneous ODE, and this is an additional response that you observe here. Now, in terms of control engineering, what we would say is the system, which is, or rather a linear system, a linear time invariant system, which is defined by these dynamics, and when it is subjected to these form of input, the response will have two segments, wherein the first segment is referred as the free response of the system. That is, even if we did not provide any forced input, or say if we did not change the status of the system in the beginning, suppose assume this pen, this writer is in my hands and it's stable, I'm doing nothing with it, and it is kept such. Now, this particular form, and if it is such for an infinite duration of time, we would say this can be defined, say, in terms of homogeneous ODE. However, if I were to make a change to it, say if I'm pushing it, or maybe pulling it, or I'm dropping it, if I'm making a change to the real dynamics of the system, I'll be representing this in form of an inhomogeneous ODE. Now, as far as control domain is concerned, it's about all about defining the dynamics of each and every physical, chemical, biological processes in and around us, and we would try to observe what exactly or how exactly the system is going to behave when we change the state of the system, say from one state to another state, or we bring, suppose a vehicle is moving and you are bringing it to rest. Now there is a force required for it, and the force that you supply, this is what we call it as excitation, or say the input, which we have already discussed very well in the first lecture. Now I would say the dynamics of a system can be defined in terms of ordinary differential equation, and the system of our concern is a linear, time invariant, causal dynamic system. And they're generally defined in terms of a linear ordinary differential equation whose coefficients are constants. Now, for such a system, and this is the second case we are observing at, and in this particular case, I'm saying, or we are claiming, that the system is defined by the dynamics pretty well, no issue, and we apply certain sort of perturbation, or say some excitation to the system, which you can observe here on the right hand side, b u of t, and the solution of this particular ODE will provide me two segments, wherein the first segment is similar to what we would have obtained when there was no input given to the system, and we'll call this as free response of the system. And the next segment that you observe here, it is because of the input that you have applied here. And this is referred as the forced response of the system. Now, as a whole, you obtain a system, you define the dynamics of system. You can choose the nature of input that you are willing to apply, based on which you can observe the behavior of the system. And the nature of input that you have selected, that depends on the real-time usage. Say while designing, come across the vehicle mechanism again. Suppose the designer, he designs the vehicle, but before going on to hitting the streets, the designer would like to check whether this designed vehicle will it sustain the oscillations on the road, or say will it sustain the stress on the roads, or if you are accelerating the vehicle suddenly, will it sustain it, or will it be broken? Will there be any damage in the vehicle or in the dynamics of the vehicle that would occur? To observe this, the engineer would be designing the vehicle in form of mathematical, say, some form of ordinary differential equation, and he will be applying certain sort of input, wherein this input is change in the state of the system. That may be a bump in a road, or maybe you're speeding suddenly. Now, this is the moment where we talk about different forms of inputs in the system that we'll see in this lecture. But as of now, we're just supposed to understand once a system is defined, we do it mathematically so that before hitting the real world, the designer is aware of how good the system is supposed to perform beforehand, so that he knows what are the negatives and what are the positives, and if there is any negative of that sort, he'll try to improvise the dynamics of system, and the same way he can design the hardware basically when before the practicals. Now, basic introduction about a Laplace transform. So we will assume that suppose we take a complex variable named as S, wherein the S can be referred as, say, sigma plus j omega, wherein both sigma and omega are real values. However, we know that this term j is technically I in mathematics, but in our domain we would be using I generally for defining current, so we choose the letter j, and j squared is equal to -1. Now we are aware of this complex variable here. I mean, we are quite well versed with complex geometry. Now, when I say the term S, now what I mean here is, say if I consider a plane, a complex plane, wherein the x-axis represents the real axis and the y-axis represents the imaginary axis. Now in such a case, if I consider any complex function in this particular plane, it will be a complex valued function of S, and which would be given by some real function of sigma and omega added with some imaginary function of sigma and omega. Now, this will make more sense when we go ahead and check what exactly this term S mean. Now, let's have a look. So let's consider I choose a function, say x of s, some certain function of s, which is s squared. Now, in this case, I can go ahead and tell, let's say for instance, if s, wherein in the previous slide we defined very well that s equals sigma plus j omega. Now, if I make a squared of that, so how would s squared be written? That's how you'd expect it to be. And j squared is -1 there, so we'll be getting um, sigma squared minus omega squared plus j times 2 sigma omega. That's what we'll get. Now here we can observe what we said earlier. Now, any function x of s in the s plane is basically a combination of certain, say, real function of sigma and omega added with certain imaginary function of sigma and omega. Now we can see here. Now this sigma squared minus omega squared, this defines the real segment, and 2 sigma omega, this defines the imaginary segment. Now when I choose any function in S domain, I would expect it to have two parts, the real part and the imaginary part. Now it is quite possible that either of these are equal to 0. That's quite possible. However, if you choose a point in the S-plane, or say if I define a function in the S-plane, it would generally bear a real function of sigma and omega and an imaginary function of sigma and omega. Now, when I choose a function, I would say that this particular function is solvable, or say analytic in a given domain, if all the derivatives of that particular function exist in the domain. However, for a particular point wherein the derivatives say it do not exist, then we'll call that particular point as, say, a pole or a singular point. Now, in the context of control engineering, um, there are certain concepts of poles and zeros and degrees, which we'll see further for sure. the roots as well, which we'll see further. But you are supposed to understand this. Say, for instance, if I take a function in the S plane, and if I say the function will be said to be analytic if at all its derivatives exist in the domain. And for that particular point in the domain, that is S domain, sigma and j omega domain, for which, say, the function is non-existent, we would call that as the singular point for the function. And for this particular case that we observed here, x of s equals s squared. Now, where exactly would be the point wherein this function would cease to exist? It would be origin. S squares, if you equate this to 0, you would be getting s equals 0. And that is exactly the point wherein this particular function will have met its singularity point, which later you would understand is also referred as the root, or maybe if it is in some sort, you can say it as a pole, or in some sort you can say it as a 0, which we'll see further for obvious reasons. However, you must understand this thing, that if I define a function, and if it is non-analytic at a particular point, we refer that as a singular point for that particular function. Now, we would notice, say, with the order of the particular ordinary differential equation, that might vary. That might be to an extended form, maybe first order, second order, third order, so on and so forth, that you would have seen in your preliminary mathematical courses. Now, the problem is we cannot invest the entire time in solving an ordinary differential equation, because the order here, unlike mathematics, when we see the real world around us, the order may be to a very high number. Now, we make use of Laplace transform here. Now, a Laplace transform, it basically represents the uh, frequency domain of a function, which actually is in time domain. Now, by this, what we do is we convert the differential equation into a simple algebraic equation, which can be solved, by simple algebraic mechanism, say by quadratic equations, or say by a simple direct solution. We can obtain that. Now, the first and foremost thing that we use Laplace transform is for simplifying the complexity that one comes across while solving differential equation. Now, if you observe this, we would often refer to the Laplace transform as, say, an integral transform. Now, in general, transform is basically from bringing one, say, function from a particular domain and dumping it to another domain. And when I say Laplace transform is it's an integral transform, what I mean is, say, if I show here, any general integral transform could be given as this sort, wherein this is the output here, and it is in certain alpha domain, some domain. And the input, which was f of t, rather I should have mentioned this guy as, say, x of t, so that it would have made more sense here. All right, assuming a function x of t which is in certain t domain, wherein let's assume to a time domain, and we're bringing it to certain alpha domain. Now we need certain multiplication factor here, which is a relation between the output domain and the input domain. Now this can be observed further. Let's have a look here. Now, any integral transform, it looks this way. See, I have a response here, x of alpha, which is in alpha domain, and I have certain input. Oops, I'm sorry for that. This should have been xt for basic understanding. However, it doesn't make a lot of difference here. It's okay. The thing that you have to consider is we are trying to change a function from one particular domain to, say, some other domain. Now, what happens here is I'll be calling this particular segment as the input, and this is the output. And here, this is referred as the integral kernel function, which defines the relation between the output domain and the input domain. Yes, this is what I'm talking about. The integral kernel is basically the function which defines the link between domains while transforming. Now let's have a look onto Laplace transform. Say if I have a function f of t which is in time domain and I'm willing to convert it to s domain, wherein this s is same as s equals sigma plus j omega, the same s which we discussed earlier. Now I would say this f of t is the input function here, f of s is the output function here, and this e to the minus st, this is the Laplace kernel or the integral kernel for the Laplace transform. Now, while explaining this particular logic, now if you are coming across signals and systems, maybe in this particular semester of study or during this period, or if you have known signals and systems, you would know. Now, say for instance, if I'm trying to convert this time domain straight away into frequency domain, say using Fourier transform. Now, what would happen? See, this S over here is basically sigma and j omega. Now, say for instance, if I substitute S equals sigma plus j omega in this particular Laplace kernel, so I would be expecting e to the power minus sigma minus j omega times t. That's what I would be expecting. And the moment you substitute sigma equals 0, wherein you want to pull the entire function as certain sort of scaled, or maybe you would say certain sort of, if you are trying to merge the entire function in frequency domain, you would be substituting sigma equals 0, and you'd observe that this particular e to the power minus st has changed into e to the power minus j omega t. And if you notice, this is the basic shape for, say, Fourier transform. That's what you'd observe. So Laplace transform, essentially it converts a time domain signal into frequency domain, wherein the domain, it has both the real and imaginary parts. Now, the moment you wish to get the entire frequency domain, you would substitute sigma equals 0, and you would observe that it's quite easy to change from a Laplace domain to a Fourier domain. This is technically out of our focus at for this particular course. However, I just gave an additional information over here. Now let's have a look further. Now the Laplace transform that we have seen just now, it's basically, you'd observe here, it is tending from, it is all the way from minus infinity to plus infinity, and we call this as a bilateral Laplace transform, as in it is existent from minus infinity to 0, and from 0 to infinity, or say plus infinity, right? However, in the course of control systems engineering, we would generally analyze a system, say from time more than or equal to 0, because negative time doesn't make sense in terms of practical real world applications. It doesn't make sense. This particular subject will be more of a practical nature. Now, since our system's dynamics is supposed to be existing for time periods more than or equal to 0, we would be using what is rather called as unilateral Laplace transform, and we would assume that this particular minus infinity to 0, it is not of our concern. So we'll be utilizing a unilateral Laplace transform wherein the range would be from 0 to plus infinity. We'd observe this thing. Hope it makes sense. Now let's come across singularity functions. Now, the study of this particular subject, it refers, or it makes, there is a special need of understanding certain sort of singularity functions, and this is a particular set of functions. Now, wherein every member of this particular set is related to the other member either by certain sort of differentiation or certain sort of integration. Now, the most significant functions that you would observe in control systems are the unit step, unit impulse, and unit ramp. Let's have a look onto them one by one. Now, unit step and unit impulse. we generally tend to say that if you consider any system in and around you, the unit step and unit impulse, these are the most general form of inputs that you would expect to occur on a regular basis to your system. Step is basically a change. An impulse is a sudden change which diminishes. Wherein the step change, it changes and it tends to stay as it is. However, an impulse, it changes at an instant and it returns back to zero. We'll observe this with some more interest today. Now, this unit step function is sometimes it's generally referred as Heaviside function, based on, to honor the engineer who basically observed it for the first time. Now, this engineer Heaviside is one way I would say he's related to the Wheatstone bridge that we come across, the electrical engineers come across in their normal curricula. The function that we are talking about is unit step and unit impulse, and we'll see how these are related. And a unit step function is basically an integration of unit impulse, or rather, impulse function is a derivative of step function. Let's have a look on what exactly we mean by that. Now, assume that I define, say, a unit step function, say in the time domain. If I'm willing to say this is the amplitude segment, this is how I'll expect the unit step to look like. Wherein, what I mean is, the function is 0 for, for time less than 0, and the function is 1 for time greater or equal to 0. Say we're talking about unit step, that's why I'm saying the magnitude would be 1, and anytime before 0 we would expect the function to be non-existent. And beyond time 0 we'll expect it to have a value of, say, an amplitude of 1. Now, suppose if I show you another case, say if I am shifting it by certain time t. Now, for this particular case, I'll expect the function to have shifted by time t. And so for this particular case, it will be 0 for time less than t, and it will be 1 for time greater or equal to t, which will be referring as a shifted function. Now, when we say that impulse function is the derivative of the step function, what do we exactly mean by that? Now, say how we define derivatives. Derivative of a particular function is basically the rise over the run. Now, if you notice here, this particular segment before 0, let's take a new page and try explaining it. Let's assume what I'm claiming here is, say if I define the impulse signal as, say, a delta signal, and I say that it is existent only at time t equals 0. I'm expecting this particular nature here. Now, if you just try to correlate the impulse input with that of, say, a step input, the shape that you will be expecting for a step input, as I'll try to draw it very really quick, this is what you would be expecting. Wherein before 0, it is the amplitude is 0, and after 0, the amplitude is 1. And at 0 too, it is 1. So for greater than or equal to 0, the amplitude is 1 for unit step signal. Now, just notice what happens here. Say this particular segment before 0, the amplitude is 0. And what can we say about the derivative? The derivative too must be 0 there. And how about the case beyond 0, more than 0? Here again, the rise is constant. The change in y is constant. And we'll be expecting the derivative to be 0 there. So whatever happens to the unit step function, maybe if I take the derivative of that, it happens in this segment at exactly equal to 0. And there you can notice the run is 0 and the rise is any number, or say it is 1 here for this particular case. So 1 over 0, and this guy will boom or shoot towards infinity. Now, to describe that, what we are saying is a unit impulse function is basically non-existent for less than 0 and non-existent for more than 0, but at time t equals 0, this guy will shoot towards infinity and to return back as time tends to increase more than 0. Non-existent on both sides, but it exists only at time t equals infinity. Now, rather, this is one way of observing it. Uh, let's try to have a look from a different perspective. Let's assume what I'm saying is an impulse function is a derivative of unit step. Can we have a look onto it in, say, the other way? Can we claim that the step input would be an integration of impulse input? Can we claim it this way? Let's just have a look. What if we try to, say, integrate between minus infinity and infinity this particular impulse function over the time? Now we know this particular function of ours, it is non-existent from 0 to infinity, from minus negative infinity to 0, and it is non-existent from 0 to infinity. However, at that particular instant 0, this guy exists. Let's have a look onto this. Say I can call this as I can call this. So maybe we all agree with this. Now between, for this particular instant and for this particular instant, we are expecting the value to be 0. But at that particular instant of 0, we have a really high value there. Now if I say that derivative of unit step is, say, unit impulse, then the integral of unit impulse would be unit step. Now I would say this particular function is technically equal to, say, u of t evaluated over minus infinity to infinity. Now essentially what I mean here is this particular impulse signal, if it is multiplied with any nature of signal, it will make it existent only for that particular duration wherein impulse exists. Now, say for instance, if I take the same signal, delta signal or say impulse signal, and if I observe, if I try to, say, multiply with certain factor of e, say e to the power, say t. If I do so, I know e of t, it basically would look like, say, this, wherein for e to the 0, we'll have a value 1 here, right? And we know that this, our impulse signal, wherein it is non-shifted, wherein I'd like to tell you that if I shift this impulse signal, if I shift it to, say, impulse of t minus t, the same curve or same plot will be shifted towards, say, certain t here. I hope this makes sense. Now, so observe this particular function here. If I'm multiplying impulse input to say certain factors, say a certain function of certain exponential function of t, e to the t. Now, this has all sort of shape here. It is existent for every value of t. However, our impulse, it exists only for time t equals 0. And what will we expect about the output of this particular expression here? Since this impulse is existent only for time t equals 0, we'll be expecting the result of this particular function to be 1. Because at time t equals 0, e to the t or e to the 0 is 1. So you would observe this, that multiplying or say getting the product of unit impulse with any sort of function will generally define you the existence of that particular function at the duration when impulse itself is existing. Later on in this course, we will be learning um, response analysis of the system for various forms of inputs, which we are observing now, and we'll try to observe how exactly a system is responding when this particular nature of input is given. Now, for this, if I say, as we have seen, unit impulse and unit step, the usage of this in control engineering is really interesting. Now, what we are willing to do is we are willing to observe a system or say design a system, define the dynamics of system in terms of ordinary differential equation, use Laplace transform, make it into simple mathematical expressions, and then try to apply these types of inputs there, unit step, unit impulse, and try to observe the response of the system. Now, when this happens, if I observe unit impulse response of a system, this technically would be same as the basic response of the system when the impulse function alone existed. What I doubt is this might not be making so much of sense to you at the moment. However, as we proceed further, mark this statement, and you would be getting more clarity on the same. Let's have a look to the next. Try and understand unit ramp signal. Now, this too is one of the singularity functions, and as we discussed earlier, singularity functions are certain sort of they are related to each other by some sort of differentiation and integration. And this unit ramp function is obtained by integration of unit step function. So we can have a look onto this. Say in the earlier slide, we represented a unit step function to look like this in time domain, wherein this is the amplitude and the function, it existed for time t greater than equal to 0, and it was non-existent for all other times. Now what if I try to integrate this particular function here? Let's have a look. So I'll be expecting the ramp signal to look like integral throughout the time, maybe minus infinity to infinity, of say the unit step function over the time. Now I know between time 0 and infinity, 0 and minus infinity, the unit step function is non-existent. So this particular expression can be shortened down in this form, u of t dot dt. And I know the value for unit step from time 0 to infinity, as you can see from here, its magnitude is say 1. Now if we go ahead and solve this, we'll be getting dt, and that would be t over the time 0 to infinity. Now with this, we could say that a unit ramp input is essentially t. Now if you observe all the three singularity functions, wherein this is step, and if I define say impulse, it existed only for time t equals 0, and if I say define ramp, It looks like this. So these are the basic shapes or basic functions that we need to understand before trying to observe the dynamics of the system for these changes. Now, for a general understanding, we could observe this. Say, uh, what do you think would be unit ramp nature of inputs for our real world control systems or for our real world systems? Now, this is something which is changing continually with respect to time. Now, this can be certain sort of, say, acceleration, which with the same magnitude, it is changing continually, and it has a linear relation with the change of time, with time. Now, if you observe a step input, a unit step input, it was non-existent before the time zero, but beyond time zero, it exists, and it exists with a constant value. Say, for instance, if you have a system, or say a normal uh, a, a pendulum, a simple pendulum which is suspended at a point, and you are holding the bob, and what do? You stretch it to one side, you pull it to one side, and you keep it held. What you have done is you have changed the state of the system, and you are keeping it held at that point. And you'd refer this as say it's a step change. You have changed it and you're keeping it still, you haven't released it yet. No, and if you are moving constantly with a constant, say, acceleration, you'd notice that in the process when you are moving the bob, the nature of input that you are feeding to this system would be a ramp. And say, for example, let's take golf. The moment the club hits the ball was static. I mean, it was at a stable condition. It was kept at a point on the surface. And the moment the golf club hits the ball, it sort of, it takes its own trajectory. It moves. That's all right. But the moment the golf club hits the ball, this is the point where we say impulse is acting. Wherein before the golf club hit it, there was no force on the system, technically zero. And at the instant when it hits, exactly at the instant when it hits, the force rise to extremes, and that's when we refer impulse function has acted on the system, which was stable at the first place before the club hits the ball. You are expected to spend some time with these sort of singularity functions before trying to go deeper into control system analysis. Spend some time, try to observe what exactly the system, how exactly the system behaves, or how exactly these functions behave when they are, say, applied to certain function, wherein all these functions are certain or one or the other form of control systems for us. Let's proceed further. Now, Laplace transform of some basic signals that we can see over here. Just have a look. Unit step 1 over s. For a ramp, 1 over s squared t to the n factorial over s to the n plus 1 e to the minus at 1 by s plus a, cos of omega t, s by squared plus omega squared, sine of omega t, omega by squared plus omega squared. You can take time and use the Laplace transformation, that integral form of Laplace transformation, and try to apply these particular signals as the inputs there, and you can obtain the respective outputs, or maybe the Laplace transformed nature of the time domain signal, that whatever you have given. Now, the most significant part of today's lecture, the properties of Laplace transform, which will help you analyze the dynamics of the system that you are choosing in say in in an easier fashion. The first property, linearity. Now we spoke about linearity already, and what exactly a linear system was. It was something which followed superposition and which followed homogeneity. Now let's go into this mathematically and let's try to understand what exactly is the linearity property. What does it suggest in Laplace transform? Now say for instance, if I take a function x1 of t, and if its Laplace transform is capital X1 of s, okay, so I'll rather say it x1 of s. And if I take another function which is x2 of t, these are in time domain, of course, and when I convert it to, say, drop it to Laplace domain, I have x2 of s is an s domain. Let's have a look. Suppose if I multiplied a constant factor with x in time domain for both the functions with certain constant factor here, I'll expect the Laplace transform of these functions to behave in a similar way, following superposition and homogeneity that you would observe here. Multiplication by certain constant term is changing the Laplace transform. It is scaling the Laplace transform basically, and addition of two different signals, it's giving the resultant as an addition of two different signals here. Now this is basically the application of superposition and homogeneity that you can see. Now, for example, let's try to solve this case here. Suppose I have a function x in time domain, which is u of t, wherein this u of t is similar unit step input that we have seen earlier. Sine 2 of t, 2 sine 2 of t plus 7e to the minus 3t. Let's try to solve this. So what I mean is, suppose these are three different segments here. First function, second function, third function. The resultant Laplace transform of this particular function will be a sum of the Laplace transform of these separate units, wherein the second function that you see over here is a product of certain constant term and sine 2t. Now what we would expect is the Laplace transform of sine 2t would be multiplied with this particular constant factor that is given here. This is what is being expressed by this particular linearity property. So let's have a look onto this. So if I were to take say the Laplace transform of x of t, for u of t I'd have 1 over s, and this 2 is a constant term, it remains as it is, and it's multiplied with sine 2 of t, sine 2t. Now that is 2 over s squared plus 2 squared plus 7 is a constant term there. Now for e to the power minus 3t we have 1 by s plus 3. Try proceeding further. 1 over s plus 4 over s squared plus 4 plus 7 over s plus 3. Now this is an example for linearity property. To remind you again, the Laplace transform of a couple of signals, of a Laplace transform of a signal, it follows homogeneity and superposition. If the initial function, or say the function in time domain, is multiplied by certain factor, and so what we will expect is the Laplace transformation of that particular signal too will be multiplied by the same constant factor, considering the the term is constant, wherein it is not a relation of a certain form of, say, certain function of t. These a and b, what we mentioned here in this particular expression, these are constant terms. And if we add two or more, say, signals, or say two or more functions in time domain, it will be similar to the addition of the functions in S domain. That's what is basically meant here by linearity. The next, time scaling. Now observe here. What exactly was the input for Laplace transformation? What did this transform do? This particular transform changed my function from time domain to, say, S domain. Rather say frequency domain, we can use that term, not an issue. So what's happening here? Say for instance, one function I take, x of t, and I'm expecting this x of t is in time domain. Yes, it's a certain function of time. Now, the moment I multiply or I scale the time by a factor of a, this is what you will expect as the Laplace transformation. 1 over magnitude of a, and the transformed function wherein the s term itself is divided by a, wherein this a is the constant by which the time scaled. Now let's have a look onto this example here. Now say for instance, if I have a function, say if the Laplace transform of x of t, certain function x of t is 1 over s plus 2. Now for this particular case, we are expected to obtain x of 4t. What is happening here? If you observe this, the first function is in a unitary relation with time, whereas this is 4 times that of the first case. Now for this, what we'll expect is the Laplace transform of x of 4t subject to, if we know what is x of t. Now we know what is x of t. So what I'll be doing, I'll be applying the above property, and I'll be getting 1 over the magnitude of 4 times 1 over, we have to observe this guy here, 1 over s plus 2. Now for this s, we are supposed to replace it by s plus a, 1 over s by 4 plus 2. What I'll be expecting here, 1 over 4 times 4 over s plus 8, wherein this 4 and the 4 cancels, and I'll be expecting 1 over s plus 8. Now I can show this maybe in, say, in a different form. Like say for instance, suppose for this particular question, we have x of t, say as x of t. Alright, so we actually have x of s here as 1 over s plus 2. Now, what is the possible time domain function for this particular expression? If I take Laplace inverse of this guy, I'll be expecting e to the power minus 2t here, right? And just read this question again. Now, if I, now this is particular, this thing is x of t. Now this is x of t in time domain, e to the power minus 2t. And what the question asks, it wants you to obtain x of 4t. And how would this expression look like? If I multiply the time with 4, I'll be getting e to the power minus 8t. And what exactly would be the Laplace transform of this particular expression? Yes, it would be 1 over s plus 8, which also is obtained by the property. You can observe it. We're supposed to give a good amount of practice to these particular properties. Let's have a look onto the next one, time shifting. Now, let's assume, similar to the previous case, we have a function x of t in certain function x of t in time domain, and we are converting it to say Laplace domain, and we have x of s. Now say if the time is being shifted here, like the case of u of t and u of t minus capital T, which we saw already in while explaining unit step and the unit impulse as well. Now what happens if I am shifting the function in time domain, say by certain factor minus t naught? Then I'll be expecting the shape. And this is really very important while understanding transportation lag. I'll say lead, that is quite a tough situation, however, transportation lag, which we'll come across later, the usage of this particular property. Now let's have a look. Try to solve this particular example using the above property. Now I'm saying that the Laplace transform of x of t is 1 over s. Now I'm expected to find Laplace transform of x of t minus 3. Try to apply this straight away. So Laplace transform of x of t minus 3 it's going to look like. Now, let's apply this property here. It's so x of s, that is exactly 1 over s times e to the power minus s into 3. That would look like e to the minus 3s divided by s. Now here this is an example of say a right shift. This is an example of say a left shift, which we'll understand as transportation lead or transportation lag in later classes. Hope it's clear. Let's go for the next one. Frequency shifting. Now this time shifting, as our initial function is in time domain, it worked there. Now this frequency shifting is basically it's in a frequency domain. Now let's have a look. Same as before, some function x of t and its Laplace transform is x of s. Now look at this particular case. If I am shifting the frequency, say observe here, observe this side. For t it represents time and this s it represents frequency. So what I'm doing in the Laplace domain is I'm shifting the frequency of the transform by certain units, and the resultant inverse Laplace, or say the resultant time domain expression for this particular function would look like this. Let's have a look. Let's try solving the below case. Now say we are supposed to find the Laplace transform e to the power minus 80 sine omega t. Now for this, there is a shift in the frequency domain that we can observe from here, this particular case. Now this is a negative shift, right? So we'll be moving forward with the second case here. Now the Laplace transform of e to the minus at sine omega t, it must look like certain form of, so let's try to get what is sine omega t's Laplace transform first. Now that basically looks like omega over s squared plus omega squared. Now what exactly is the frequency component here? This s, it bears sigma and j omega. Now this is the frequency component here. So for this s we are supposed to shift it again by negative a factor. So what will happen here? The resultant would look like this: omega by s plus a whole squared plus omega squared. That's how it's going to look like. For the previous case, we noticed shift in time domain. And for this case, we are noticing there is a shift in frequency domain. You have to observe that. Let's move forward. Differentiation. It's really very important. Suppose I have a function x of t whose Laplace transform is x of s. What if I take the Laplace transform of differential of x of t, first order differential of x of t? Now this is the shape that you are going to observe, wherein this x of 0 negative, it is the initial condition of the system. It is the initial condition. What exactly was the behavior of the system before the change was applied? Now this double differential of x of t, s squared xs minus sx naught minus x. You observe this particular function here. It's the differential of the initial condition that you have to notice here, right? And let's try solving the following expression. Say if I wish to get the Laplace transform of this given differential equation, and you would notice this is an ordinary differential equation, inhomogeneous differential equation with constant coefficients. So this basically is representing one of the linear time invariant system, and these are the basic examples that you would consider. These are the basic shapes or types of expressions or equations that you would consider while defining the control system in our daily life, or maybe for this particular subject. Let's try to solve it. Now for this, if I get a Laplace transform of this particular segment. Say we are supposed to use the linearity property and we are supposed to solve them each and then add them together. Now for this particular expression, what we would be getting is s squared x of s minus s, the initial condition of x, minus x dash, initial condition of x. Now for the second expression, we would be getting plus 6s x of s minus the initial condition of x. For third expression, 16 x of s, and the final set 16u of t, that would be 16 times the unit impulse, unit step, that would look like 16 over s. Now in the question it was given that the initial conditions are 0. So what we mean is this factor returns 0, this factor returns 0, this factor returns another 0. So the Laplace transform of this particular expression, it would look like s squared x of s plus 6s x of s plus 16 x of s equals 16 over s. Now from here, if we take x of s out in common, we can also obtain s squared plus 6s plus 16. That's equal to 16 over s. And the final expression, if I am trying to get it in terms of x of s, I'd observe it to be 16 over s times s squared plus 6s plus 16. And this is what we would call as a transfer function in for our later usage. So this particular property of differentiation is really important. You are expected to solve some of these kind, and maybe in the next lecture we'll be doing certain hands-on with these particular properties and trying to solve some Laplace transforms, some inverse Laplace transforms. We'll try to have a look onto it. Now let's have a look onto the next property, convolution. Now convolution in time domain is basically equivalent to multiplication in S domain. Now let's have a look. Suppose if I have two functions here, x of t and g of t, these are in time domain, and their Laplace transforms are x of s, g of s. Now convolution of them in time domain, wherein convolution, this is how it looks like. I say x of t convolved with g of t, and this looks quite complex when you are trying to solve it in time domain. Whereas in Laplace domain, convolution is directly equal to the multiplication of the functions. If I taken x of t and g of t and assuming their Laplace transforms to be x of s, g of s, then if I convolve x of t and g of t, the product will, the result would be same as x of s multiplied with g of s. That's what is explained here. We have little to no usage of this particular property here in controls. However, there is a good chance that sometimes some complex questions may be framed for which you can utilize this property. And I assure that we'll be having a look onto some sort of these kind of questions as well in our series. Here comes the summary. Now, today we tried to have a look onto the basic mathematical prerequisites that is required to further go deeper into control system analysis or maybe design of control system. Now, today we saw ordinary differential equations, or rather, we revised our concepts of ordinary differential equation. We saw what exactly should be the type of ordinary differential equation that a control engineer must be worried about. We revised Laplace transforms. We saw certain types of singularity functions. We saw unit step, unit impulse, unit ramp. We checked Laplace transform some basic functions, and we observed the properties of Laplace transform, ranging all the way from linearity, uh, time shifting, frequency shifting, convolution, differentiation property. Wherein all these properties are they are of profound usage in our course. So with this, I leave you with a note and with a request that you go ahead and have a look onto these nature of signals and try to be familiar with uh, these properties, so that the designing and the analysis part of control systems for us for later classes becomes simpler. Because when we solve a real system, we would not be doing it stepwise. Rather, initially, for example, if I take the case of the differentiation property that we just saw now with the second order system, in the initial phase itself, we would be aware that the initial condition was 0. So we would not mention it and then equate it to 0 and then um, take them off the equation. No. For the first step itself, we'll be removing it. Rather, we would go ahead with certain shortcuts. And this is really important for you. It is really important for you to understand or be familiar with these properties and these nature of signals, or say functions, so that the life becomes simple in the upcoming classes. Thank you for listening. In the next lecture, we'll be moving forward with certain practice of Laplace transforms and inverse Laplace transforms, so that it's simpler for us for later classes. Thank you.